Ladies and gentlemen, welcome back. It's Ripley here, and we're going to do the last section of the fall semester. It's 9.3. It's called Demoivre. So this is Moivre's theorem, but it's Demoivre. French guy. No, clearly Italian, right? I'm kidding. But before we do that, let's have a quick little review about complex numbers. So we need to talk about the complex plane. And this may feel like a huge head shift as far as, wait a sec, why are we talking about the complex plane? Really, I'm hoping that at some point there was just a little kernel of, with the whole idea of polar coordinates, polar graphs, where you were like, why are we doing this? I mean, the function, the Cartesian plane works perfectly well. Well, not quite as well when we start talking about graphs like this, right? Because we can't really do functions that behave in this manner, right? So it does have a purpose. It gives us the ability to make to clearly define and concisely define crazy looking graphs that don't fit our traditional definitions of functions. In other words, put 1x in, get 2 or get 1y out. Let me click back to that. I mean, could you imagine trying to define this as a function? For this value of x, for x equals -1, you'd get 1, 2, 3, 4 values of y. That's not very functional. I know, it's so lame. All right, so let's talk about the complex plane real quick. Let's see what you remember. Remember, in the complex plane, it works just like the Cartesian plane, except on the x-axis, we're talking about real numbers, and on the y-axis, we're talking about imaginary numbers. Remember, I is equal to the square root of -1. All right? Now, a complex number is any number that can be written as x plus yi, and we typically wrote these like as z. So z represented a complex number. So if I want to write z equals 4 minus 3i, well, let's go 4 plus 3i because that's how I drew it. Then I just go over 1, 2, 3, 4, and I go up 1, 2, 3, and I get this point right here. So this would be 4 plus 3i, and it's represented by that point. Now, if you remember, there was something called a modulus. And the way in which the modulus was written is it was written as the absolute value of z. And the way that we found it is we took, really, in this case, absolute z, in this case, would be written as the square root of 4 squared plus 3 squared. And the reason why is we made this nice little right triangle. So Pythagorean's theorem still applies in the imaginary plane, right? So we know that its length is the square root of 25, which is actually known as 5. Now, in general, the way that we could find it, now, I don't know how many of you are going to remember this, excuse me, but the way that we can find this is we can take the square root of z times, remember that thing? What was that thing called again? Remember, if I have a z bar, so if z equals x plus yi, remember what z bar was? It was the conjugate. So x minus yi. And if you think about it, this right here is just the square root. Again, this is just review, so don't panic. I know you've seen it. If I go x plus yi times x minus yi, this is the difference of two perfect squares. So I end up with the square root of x squared minus y squared I squared, but I is the square root of -1. So when I take the square root of -1 squared, I get -1. So this turns into the square root of x squared plus y squared. It's the same thing. Now, think about that for just a second. If I take z equals x plus yi, can't I rewrite this using polar ideas? I know that x, I mean, remember, we know we have very easy things to deal with polars. Now, we do crazy things with them, but we still have some pretty easy things to deal with. I know that x equals r cos theta, as opposed to Ross theta, sorry, r cos theta, and y equals r sine theta, right? Which means that we can rewrite z as, rather than as x plus yi, I can rewrite this as, well, look, r cosine of theta plus r sine of theta times I. Now, if I factor out the r, the way that I'll write this is r times cosine of theta plus I sine of theta. And the reason that I do that is it keeps the I out of the angle. Now, you will sometimes see this written, and I'll let you use this notation if you like it. If you think about it as cos I sine, you'll sometimes see this written as R times cis of theta. And I'll probably jump back and forth between the notation, excuse me, just because it's fun. Excuse me, just because it's fun. All right. Now, let's play. Let's just have some fun here for a second and look at what happens. Because what we're going to do is, like I said, we're going to use Demoivre's theorem, believe it or not, combined with our ideas about the polar plane, using polar coordinates, using polar expressions. We're going to use this to make our lives easier in different ways, in ways that you may not have really seen coming. You wouldn't anticipate these, but they're neat little tools, all right, other than just being able to graph swoop-de-loop-de, hoop-de things. All right, for example, watch this. If I let Z1 equal, let's go R1 cos theta 1 plus, whoops, let's go R1 times cos theta 1 plus I sine theta 1. Now notice this theta is always the same because it's this theta. And if I let Z2 equal R2 times cos theta 2 plus I sine theta 2, then let's see what happens if we start multiplying and dividing these things. Okay? In other words, what happens if I do Z1 times Z2? Now, please recall, this is not new. We know how to add, subtract, multiply, and divide complex numbers, but we got this new thing we can play with. Let's see what happens. Well, this is going to turn into R1. Now, hopefully you can visualize this. R1 times R2 times cos theta 1 plus I sine theta 1 times cos theta 2 plus I sine theta 2, right? Nothing to it. Now let's actually go through the process because this is pretty neat. R1 times R2. Now let's see what we get here. We're going to end up with cosine of theta 1 cosine of theta 2. Okay? If I distribute, that's all I'm doing. I'm using the distributive property, right? Plus I sine of theta 1, whoops, I sine of theta 2, excuse me, cosine of theta 1 plus I sine of theta 1 cosine of theta 2. You see how those switch when I do this underneath. And then look close. If I go I sine theta 1, I sine theta 2, I'll get I squared, which is negative 1. So minus sine of theta 1 sine of theta 2. Again, that's produced because that I and that I, when they multiply together, they make negative 1. Now, I'm going to group these in what may appear to be a strange formula, but watch, or in a strange way. I'm going to group this as, excuse me, this is going to be the cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. And then watch this, you're going to love this. Plus, now notice that this term and this term both have an I in it. So what I'm going to do is I'm going to factor out the I and watch what happens. I end up with sine theta 1 cos theta 2 plus sine theta 2 cos theta 1. Boy, I'm getting tight in there. Now look close. Check this out. If I group this, whoop, look, what do you see as cos theta 1, cos theta 2 minus sine theta 1, sine theta 2? Do you remember what that was? This is cosine of theta 1 plus theta 2. I'm just using that identity, right? Cosine of theta 1 plus theta 2 is cos theta 1, cos theta 2 minus sine theta 1, sine theta 2. Also, what is sine theta 1, cos theta 2 plus sine theta 2, cos theta 1? Well, hopefully, I'm going to do this in a different color. I'm starting to get crammed in down there. Hopefully you see this as, this little chunk right here as sine of theta 1 plus theta 2, which implies that this whole thing turns into R1, R2 times, you ready? Cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And look at here. I guess another way that you could write this is R1, R2, cis theta 1 plus theta 2. So what that means is if I rewrite, remember these are polar representations of complex numbers, right? If I rewrite these and I multiply, then all that I have to do is add my theta 1 and theta 2's together and then stick them in the cos, add my theta 1 and theta 2 together, stick them in the sine, and then multiply my r's. Well, that's pretty easy, right? Now, how about this guy? We won't prove this one because this one's a little bit nastier and time-consuming to prove, but it's not terribly difficult, just because what you would do is well, we won't worry about it. Okay, so again, if Z1 equals R1 times cos theta 1 plus I sine theta 1, and Z2 equals R2 times cos theta 2 plus I sine of theta 2. Remember, these guys, just think of this as being x1 plus y1 I, and this is being x2 plus y2 I, right? That's how we represent them. Excuse me. Then if I take z1 and I divide it by z2, now watch what happens. This is a piece of cake. I just take r1 and divide it by r2, just like we would expect. And then what would I do? I'm going to go cosine of theta 1 minus theta 2. Think about your properties, right? Your exponential properties, right? Plus I sine of theta 1 minus theta 2. So Demoivre, this guy Demoivre, clearly he's Hawaiian, right? Kidding. It's so stupid. Demoivre comes along and he says, wait a second, maybe I can make a name for myself by coming up with a general rule. In other words, what if I let z equal r times cosine of theta plus I sine of theta, right? Well, what can I come up with a formula for z to the n? Well, watch what he did. Here's all that he did. Well, this is z to the first. How about z squared? Well, what's z squared going to be? It's going to be z times z. And according to our rules, z times z is, remember, z is just r cos theta, right? So this is going to be r squared times cosine of theta plus I sine of theta plus theta, right? So this turns into r squared times cosine of 2 theta, right? Theta plus I sine of 2 theta, theta plus theta. Okay, how about z cubed? Well, isn't that just z squared times z, which is what? All right, think about what's going to happen here. It's this guy, which I just did, times the original z, so I'm going to get an r cubed times cosine of 2 theta plus I sine of 2 theta plus theta. And look at what I get. Easily proven, right? R cubed is cosine of 3 theta plus I sine of 3 theta. So guess what? What's z to the n? It's easy. It's r to the n times the cosine of n theta plus I sine of n theta. Isn't that awesome? Now, the proof of this is a little bit nastier because I just proved them for integers and it was real simple and it was fun to do. Okay? However, this gives you an idea about how it was done, and it's really, really useful. And this guy made a name for himself into eternity because he was able to see a cool little pattern. He didn't just see the pattern. I mean, mathematicians had been playing with these patterns for a really long time, and he was just the one that said, wait, I got it. And this is what he came up with. This is Demoivre's theorem. Right here. Isn't that easy? Nothing to it.